Hello everyone, let's review the group theory semester of the Algebra mod. First, we would like to review the definition of a group, but to do that, we need to define binary operation. A binary operation on a non-empty set S is a function star from S cross S to S. So, now, a group G with star is a set G with a binary operation star which satisfies three conditions abbreviated to ANI. First, we require a star to be associated, i.e. A star in bracket B star C is equal to A star B in bracket star C for all A, B and C in G. Next, we require a neutral element E in G such that E star A is equal to A, which is equal to A star E for all A in G. We also require that for all G in G, there exists an inverse G dash in G such that G star G dash equal to E, which is equal to G dash star G. This definition of a group leads to the solvability of equations lemma. It says that if G with dot is a group and A and B are G, then there exists a unique X and Y such that A dot X equals B and Y dot A to B. This means that if A dot X equal to A for all X in G, then X is equal to E, the unique identity element, also called the unique neutral element of G. Similarly, if A dot X is equal to E or X dot A is equal to E for all X in G, then X equal to A dash, the unique inverse of A, denoted A to the minus 1. Therefore, we get the inverse of a product lemma. It says that if G with dot is a group and A1 to AN in G, then A1 dot AN inverse is equal to AN inverse times all the way up to A1 in. Next, let's discuss some remarks for group. For a group G with dot, the order of G is the cardinality of the set G. Also, a type of group is a commutative or abelian group, which is where dot is also commutative, i.e. A dot B is equal to B dot A for all A and B in G. Another type of group we want to discuss is a symmetric group, but to motivate it, we need to discuss permutations. For a set X with a positive integer n number of elements, a permutation of X is a bijective function pi from X to X. Hence, there are exactly n factorial permutations of X. We can write the permutations using cycle notation. For example, pi equaling I to the pi, all the way up to I to the pi to the s, j to the pi, all the way up to j to the pi to the t, and all the way up to k to the pi, all the way up to k to the pi to the u, which means that I maps to I to the pi, which maps all the way up to I to the pi to the s, which loops back round and maps to I, and j maps to j to the pi, which maps all the way up to j to the pi to the t, which maps to j again, all the way up to k, maps to k to the pi, all the way up to k to the pi to the s, then loops back round and maps to k again. Note that this notation is unique only up to cyclically reordering the elements in each cycle, and up to reordering the cycles arbitrarily. Now, let's define a symmetric group. Let sim X be the set of all permutations of X, and let circ denote the binary operation of the composition of function, i.e. pi circ psi maps from X to X is the map defined by I to the pi circ psi is equal to I to the pi to the psi. Then sim X with circ is the symmetric group on X. It is also called the symmetric group of degree n, denoted by sim n if X has size n. One remark is that a symmetric group is abelian only if n is equal to 1 or 2. Next, let's discuss the results for the powers of elements of group. Let G with dot be a group with neutral element E, and let G be an element of G. Then the powers of G are G to the naught, which is defined to be E, and G to the I is defined to be G times G to the I minus 1, and G to the minus I is defined to be the inverse of G to the I for all integers I greater than or equal to 1. Hence, we have that G to the A times G to the B is equal to G to the A plus B, and G to the A to the B is equal to G to the AB for all A and B in G, as we might expect. Now, let's discuss how to visualize some types of groups using group tables, also known as Cayley table. Let G with dot be a finite group and enumerate G as G1 is equal to E all the way up to Gn, where E is the identity element of G. In the ijth position of the table, we write the product G sub I times G sub J. So, the table looks like this. For these group tables, we have the Sudoku property. It says that in the group table of G, each row and each column contains every element of G exactly one. Also, G is commutative if and only if the table is symmetric about its diagonal. Next, Next, let's discuss subgroup. If G with dot is a group and H is a subset of G, then H with dot is a subgroup of G if H with dot is a group, where dot is the same binary operation as on G, so A dot B has to be in H. If H with dot is a subgroup of G, we often simply write H is a subset of G and say that H, a subset of G, are grouped. To tell whether a subset is a subgroup, we use the subgroup test. It says that if H is a non-empty set, then H with dot is a subgroup of G with dot if and only if for all A and B in H, we have that A dot the inverse of B is also in H. Hence, we have a handy result subgroup. It says that if G with dot is a group with subgroups H and K, then H intersect K is also a subgroup. Next, let's discuss subgroups generated by a set. Let G with dot be a group and let X denote a subset of G. Let the set of all Hi, where I is in I, be the family of all subgroups of G containing X. Then X in angled brackets is equal to the intersection over all I in I of Hi is the subgroup generated by X. If X is the empty set, we let the set generated by X equal the set containing just the identity element, which is we call the identity subgroup. Also note the notation that instead of writing in angled bracket and then the set containing X, Y, Z, etc., we instead more briefly write in angled brackets X, Y, Z without the set bracket. Also note that we have that the set generated by X is equal to the set of all G1 to the power epsilon 1 times all the way up to Gn to the power epsilon n, where Gi is in X and Ei is in the integers. So if G is in G, we have that the set generated by the element G is equal to the set of all G to the power I, where I is in the integers, which is the cyclic subgroup generated by G. The order of the element G is the order of the subgroup generated by G and is denoted as the cardinality of lowercase g is defined to be the cardinality of the subset generated by G. Now, let's define a cyclic group. We say that G is cyclic if there is some G in G such that G is equal to the cyclic subgroup generated by G. If G is a cyclic group of order n, we also write that G is equal to C sub n. Now, let's discuss some results for the order of element. Let G with dot be a group and let G be in G whose order is finite. Then G to the order of G is equal to the identity element and the order of G is the least positive integer with this property. So the inverse of G is equal to G to the power of the order of G minus 1. Also, suppose there is H in G with finite order such that GH is equal to HG. Then the order of GH is finite and divides the lowest common multiple of the order of G and the order of H. Therefore, if G is in the symmetric group of degree n and is the product of disjoint cycles of length n1, n2 all the way up to nt, then the order of G is equal to the lowest common multiple of n1, n2 all the way up to n to the t. Also, we have the result that if H is a subgroup of the integers, there exists an integer d which is greater than or equal to 0, so that H is equal to dz. Next, let's discuss the groups of symmetries, which shouldn't be confused with the symmetric group on a set. Let A be some geometric or combinatorial object defined on a set X of vertices. Informally, we define the symmetry group of A, also called the automorphism group of A, to be the set of all permutations in the symmetric group of X which preserve A. It is denoted by aut A. Let's give an example of a group of symmetries. For a cube C, the full symmetry group or C is the symmetric group sim A on the set A of the four opposite vertex pairs of C. Next, let's define the dihedral group, which is a type of group of symmetries. Let n be an integer which is greater than or equal to 3, and let R and F be in the symmetric group of degree n be permutations such that R is equal to the cycle 1, 2 all the way up to n, and F is equal to cycle of 1, 2 with n, 3 with n minus 1, all the way up to n over 2 with n over 2 plus 2, and then n over 2 plus 1 when n is even, or F is equal to the cycle of 1, 2 with n, 3 with n minus 1 all the way up to n plus 1 over 2 with n plus 3 over 2 when n is odd. Then the group D sub n is defined to be the group generated by R and F and is the dihedral group of degree n. The subgroup R, which is the subgroup generated by R, is the rotation subgroup of Dn. Hence, let's discuss some results for dihedral group. We have that D sub n has order 2n and Fr is equal to the inverse of R times F, and the cyclic rotation subgroup R has order n. Also, Dn is the full symmetry group on a regular n-gon. Next, let's discuss some other ways to define dihedral group. We can define the dihedral group Dn as the set generated by R and F such that R to the n is equal to E, which is equal to F squared, and Fr is equal to the inverse of R times F. Where Fr is defined to be the set of all Fr where R is in R, we have that Dn is equal to R union Fr. Note that Rf, which is equal to the set of all Rf where R is in R, is equal to Fr because Fr is equal to the inverse of R times F. Further, we can define the dihedral groups as Dn is equal to the set of all F and F dash such that F dash squared is equal to E, which is equal to F squared, and F times F dash to the n is equal to E. Next, let's move on to discussing Lagrange's theorem. It says that if G is a finite group and H is a subgroup of G, then the order of H divides the order of G. To see this, we need to define coset. Let H, a subset of G, be groups, not necessarily finite. Let G be in G. Then the set GH, defined to be GH for all H in H, is the left coset of G in G for H. Similarly, HG is defined to be the set of all HG for H in H, and is the right coset of G in G for H. If G star is any element of GH, we also say that G star is a representation of GH. This definition of cosets leads to some useful results. Let H be a subset of G be groups, and let G and G star be in G. Then we have that either GH is equal to G star H, note this can happen even if G does not equal G star, or GH intersect G star H is equal to the empty set. Also, GH equals G star H if and only if the inverse of G times G star is in H. Similar results hold for right coset. Therefore, the left cosets or right coset form a partition of G. Note that EH, which is equal to H, which is equal to HE, is the only coset that is a subgroup, as is the only coset containing the identity element. Next, let's define the index. The number of distinct left cosets of H in G is called the index of H in G. It is denoted by the cardinality of G colon H. Now, let's discuss the converse of Lagrange's theorem. In general, the converse of Lagrange's theorem is false, i.e. we cannot say that if D is a divisor of the order of G, then there is a subgroup of order D. However, some partial converses do exist. For example, if G is a finite abelian group, then for every divisor D of the cardinality of G, there is a subgroup of order D. Also, if G is a finite group and D is a power of some prime dividing the cardinality of G, then there is a subgroup of order D. Next, let's discuss some applications of Lagrange's theorem. One such application is that if G is a finite group and G is in G, then the order of G divides the order of G. Another application is that if the order of G is prime, then the set containing just E and G are the only subgroups of G, and G is equal to the subgroup generated by G for all G in G which are not the identity element. Another application is that if A and B are subgroup of the finite group G, then the order of A intersect B divides the greatest common divisor of the cardinality of A and the cardinality of B. Yet another application is that if A is a subset of B and is in turn a subset of G, and they're all grouped, then the index B colon A times index G colon B is equal to the index G colon A. So if the index of G colon A is prime, then A equals B, or B equals G. Next, let's discuss quotient groups. So first, let's give an informal description. Let H be a subgroup of G, and let G bar equal the set of all G8 for G in G be the set of all distinct coset of H in G. For quotient groups, we need to think of each coset as a new single element of this new set G bar. Before we can define a quotient group, we need to define a normal subgroup. Let H be a subset of G and let them both be groups. Then H is a normal subgroup of G, denoted like this if GH is equal to HG for all G in G. In this case, we denote the set of all left or right cosets of H in G by G over H. On this set, we can define a binary operation by GH circ G' is equal to G times G' for all G and G' in G, which is a way of multiplying cosets. Now we can define a quotient group. If H is a normal subgroup of G, then G over H with circ is the factor group or quotient group of G modulo H, or just G over H. Now let's discuss some results for normal subgroups. Let H be a subgroup of G. Then H is normal in G if and only if G inverse HG subset of H for all G in G, i.e. G inverse HG is in H for all G in G and H in H. Also, if H is normal in G, then the order of G over H is equal to the index of H in G, and if G is also finite, then the order of G over H is equal to the order of G divided by the order of H. Next, let's define trivial normal subgroup and simple group. If G is a group, then the set containing just the identity element and G are normal subgroups and are trivial normal subgroup of G. If G does not equal 1, and if there is no other normal subgroup, then G is simple. Now, let's move on to defining group homomorphism. Suppose that G is equal to G with dot, and H is equal to H with circ are both groups, and suppose that phi goes from G to H. Then phi is a homomorphism of groups if phi of A dot B is equal to phi of A circ phi of B for all A and B in G. Next, let's define the types of homomorphism. Suppose that phi from G to H is a homomorphism. If phi is injective, then phi is called a monomorphism. If phi is surjective, then phi is called an epimorphism. If phi is bijective, then psi is called an isomorphism. An isomorphism where G is equal to H is called an automorphism of G. Then let's give some remarks for isomorphism. If G and H are groups, and if there exists an isomorphism phi from G to H, then G and H are isomorphic. We denote this like this. Note that we have that the inverse of phi from H to G is also thus an isomorphism. Now let's discuss some results for homomorphism. Let phi from G to H be a homomorphism. Then phi of the identity element in G is equal to the identity element in A. And for all G in G and Z in the integers, we have that phi of G to the Z is equal to phi of G all to the Z. If psi from H to I is also a homomorphism, then psi circ phi from G to I is a homomorphism. Now let's define the kernel and the image. Let phi from G to H be a homomorphism. Then ker phi, defined to be the set of all A in G such that phi of A is equal to the identity element in A, is the kernel of phi. And im phi, defined to be the set of all X in H such that phi of A is equal to X for some A in G, is the image of phi, which we also denote as phi of capital G. Now let's discuss some results for kernels and images. Let phi from G to H be a homomorphism. Then the kernel of phi is a normal subgroup of G, and the image of phi is a subgroup of H. Also, phi is injective if and only if the kernel of phi is equal to just the set containing the identity element of G. Now let's move on to the first isomorphism theorem. Let G and H be groups. Suppose that phi from G to H is a homomorphism with kernel K. Then phi bar from G over K to the image of phi, given by GK goes to phi of G for all G and G, is an isomorphism. Hence, let's give some results for cyclic group. Suppose that G equal to the set generated by G is a cyclic group. Then every subgroup U not equal to the set containing just the identity element of G is cyclic. and of the form U is equal to the group generated by G to the D for some D. And if G is infinite, then G is isomorphic to the group of the integers with addition. Also, if the cardinality of G is equal to n, then G is isomorphic to Z mod nz, and G has exactly one subgroup of order m for every m a divisor of n. Now, let's move on to defining group actions. Let G be a group, and let omega be a set. Then an action of G on omega is a map mu from omega cross G to omega, such that if 1 is the neutral element of G, then mu of alpha 1 is equal to alpha for all alpha in omega, and if G and H are in G, then mu of alpha with GH is equal to mu of alpha with G with H for all alpha in omega. Now we can show that the actions of a group G correspond uniquely to homomorphisms from G to the symmetric group on some suitable set. First, we have that if mu from omega times G to omega is an action, then phi from G to the symmetric group on omega with alpha on phi of G mapping to mu of alpha with G is a homomorphism. Conversely, if phi from G to the symmetric group on omega is a homomorphism, then mu of alpha with G, defined to be alpha on phi of G for all alpha in G and G in G, defines an action. Now, let's discuss some notation for action. If mu is an action, and if the context is clear, we write a to the G instead of mu of a and G, and we say also that G and with omega is an action, or that omega is a G set. If 1 is equal to the identity element of G, the two conditions being an action are that alpha to the 1 is equal to alpha for all alpha in omega, and alpha to the GH is equal to alpha to the G to the 8 for all alpha in omega and all G and H in G. Now, let's define some terms relating to action. If beta is in omega, then beta to the G is defined to be set of all beta to the G for G in G, and is called the orbit of beta under G. If there is some beta in omega such that beta to the G is equal to omega, then G with omega is a transitive action, or omega is a transitive G set. The kernel of the action is the set K of all elements G in G, such that mu of alpha with G is equal to alpha for all alpha in omega. We say that the action is faithful if K is equal to 1. If G with omega is an action, then the cardinality of omega is the degree of the action. If G with omega is an action, and if alpha is in omega, we let G sub alpha to be defined as the all G in G such that alpha to the G is equal to alpha. We call this the stabilizer of alpha in G. Now, let's discuss some results for actions. Let G act on a set omega, and let alpha and beta be in omega. Then G sub alpha, the stabilizer of alpha, is a subgroup of G, and we have that alpha to the G equals beta to the G, or alpha to the G intersect beta to the G is equal to the empty set. For any G in G, we have that the inverse of G times G sub alpha G is equal to G sub alpha to the G. Also, the kernel of the action is a normal subgroup of G, as is the kernel of the corresponding homomorphism from G to the symmetric group on omega. These lead to the orbit stabilizer theorem, abbreviated to OST. Let G act on a set omega, and let alpha be in omega. Denote the stabilizer of alpha by H. Then there is a one-to-one correspondence between the G orbit of alpha and the collection of all right cosets of H in G. In particular, we have that the cardinality of alpha to the G is equal to the index of H in G. So, when G is finite, we thus have that the cardinality of alpha to the G times H is equal to G. And, as ever, thank you for watching.